Okay, hello. Anyway, welcome to here. Very happy to see so many people around, and I will shortly tell about my background a little bit, and then I have done a lot of research on different topics, but then especially I will go more to this wind navigation simulation tool, one very interesting tool we have been developing and also applying to Estonia. So that's my background. So I started, even though I'm young, I started as a Master of Science in 1979. I graduated, I was in VTT for a while, one year in London. Then after that, I was a bachelor's student in Pentti, and then I did my doctorate in 1994. I taught politics. And after that, I worked a long time as a postdoc. It was done in TKK, about 7 years as a postdoc. I was doing all the work for Wilson Wars. I did nothing, I did everything for it. Because the salary I got the work. It's a good deal. The postdoc won't be too long, 7 years too long for a postdoc. 2 years maximum, because I did everything and okay. But now, after that, I went to the materials for 3 years. I was very big European Union project, got 39 million euros from the European Union. And we had only 4 years' time to spend it. One materials, Tantieri, Atlantic, Fincantieri, and Meyer, Papenburg. And we were there, and in 4 years, we spent 40 million euros. So it has a very lot of work. About ship design, ship production, and so it was very interesting European Union projects. I was sort of a main scientific coordinator, so I'm the only one who was reading all the papers, because I was checking all the deliverables. There was about 100 deliverables, and in that time I was the best expert in ship design production in Europe. Nobody else has these papers. I had to read it because I was commenting and okay. And then finally in 2006 I got back to the TKK, and then I was professor of marine traffic safety. And I'm still working on until 2022. So I'm still a senior advisor, but that's my background. I have a lot of work in ice loading, but I had also, when I started my career as a bitumen carrier, I was measuring thermal stresses, and we put 170-degree bitumen in the tanker. What happened to the structures? That was my young scientist work in London. And I made a final development about bitumen carrier and very hot cargo. And then we had to make little thermocouples. We went to Curacao Island, put thermocouples on the bitumen tanker, and from Curacao Island we went to New York sailing, and I was measuring the thermal stresses. So I know plus 200 degrees, and now I know also minus 40 degrees. So between these degrees, I'm still okay. From minus 40 to plus 200, but above that, that's not good. And what I have done my own research topic, I have really done a lot of work on ice flow statistics. That's my own big hobby. Still one project ongoing with South Africa, Antarctica. And then I was the postdoc in TKK, was doing a lot of work on light structures, building light structures, and then in 2006 I came. Marine safety was this what I'm now ongoing. So this is a big picture. I've been trying to understand 40 years ice flow statistics, because when you measure ice flow, this is about 30 seconds, so 3 hours. And since it's 3 hours in ice, you get this kind of a ice loading on the hull, random. I know something after 40 years, but still a lot of work to do. It's very complicated problem, this ice flow statistics. And I was very happy to be part of one very big European Union report about collision, because that's also very they got TNO in Netherlands, they got a lot of money to make full-scale testing about structures, and then there's a big about the story. Because if you put standard structures in a big hole, you cannot show there's no really. But on the left up, you can see that standard structures, if you hit by this kind of a collision, it's a big hole. But I was developing the kind of a steel hanging panels. I optimized the structures, and after that collision, there was no hole, so it was a surprise that it can be done. It could be done. So, and this is actually a famous test. But although you might know Christian Taaperi and Mikael Pöperät, they both use this data when they doctorate. So very famous.
Sorry. Do you hear me?
Yeah.
The problem is that for us the slides have not changed when you switch it. That's So we're still seeing first slide. I don't know why.
Can you let loose how to do it? I know because the expert here who can. So I put it on this form. Now you can see maybe.
Actually, the picture is the same, but
Sometimes happens. I never know why.
It's first.
maybe.
Because it's not shared.
Yeah. Shared.
Show.
Okay.
No, you need to just first open it like a slideshow.
Okay. Now it's much better. Yeah.
Okay.
But they still looking like that. Okay, can I?
Yes, I see right now all the slides list, but.
Because I share the whole screen. It's okay.
Yeah.
Okay.
Now you can see all the. Yeah.
Yes, now it's good. Yeah, very good.
Okay, this is not that slide you lost, and this is the video is interesting. If you can see the very interesting full-scale testing, can you see the video? But you don't know I know that you don't remember that. Okay.
Yeah, very good. We see. Yeah, very good.
So they also spend a lot of European Union money to make very interesting testing by TNO in Netherlands. Okay. But that's once more say that Mr. Christian Taaperi and Mikael Pöperät you might know very well, so they doctorate on that topic. Of course, I have a lot of networks. And I have been 40 years on this area, so of course I know every naval architect in academic life in Europe. In the USA, mainly Michigan, in Canada Memorial University. In Brazil, I know Rio, and I know this Rio and Sao Paulo, and then South Africa, I know Cape Town. And China, I know Dalian, Harbin, Wuhan, and now also Jiantong in Shanghai. Some contacts to Singapore, some contacts to Thailand, Australia. In Japan, I know with the ice guys. So that's the background. And of course, been quite active on publications, especially when I got my professorships. You can see that I started slowly. About 2010, only very practical work, European Union project and reports, even though very important reports, but no publications. But then I got my own research group in TKK. We started to make publications, and it's still growing. I have last year 1,300 citations, and this year so far 1,000. So it might go down a little bit, but about 7,000 citations in my 1848. Educated 31, 35 master thesis on my professor time, 13 doctoral thesis. Actually, 2 new is coming 13th December, 1 new doctor in Aalto, and 1 more is coming next spring. Then I have 15, and after that, next ones are in Taltech. So 2 more in Aalto, and next ones hopefully in Taltech. I have educated 6 professors of my postdocs, my doctoral students. They are in Finland, Poland, Canada, Brazil, China at the moment, and of my next professor hopefully is also in Taltech. So my duty here is to educate my 7th professor who will start in Taltech, so in 2 years. And that's it. So let's see how, as I said to somebody that when I make my own research group in TKK, it took 6 years to get it up and running. So 6 years the minimum to get a very good group. So the plan is that after 6 years, I will have a 1-year professor here. So let's see. That's the time to start from when you don't have much activity. So we're very active on European Union projects, Academy Finland, European Union, and so on. I was chairing one Center of Excellence with Loistic Institute Foundation, and some teaching as well. So that was that slide. Any questions about my background before I go to the topic today?
No questions. Your background is amazing.
Important to have a very good book. You need good people to help you. Alone you can do nothing. Okay, I can see nothing. Can you change the whole screen because what are difficult thing? Okay.
No, it's right one.
Now we can see. Okay. Okay, then I will show one example about my research topic. It's simulation tool for wind navigation support, decision support in Baltic Sea. We have done it in Finland and Sweden and also in Estonia. It's an example about results, and I have been kind of a coordinator, but there are some other people, especially in Aalto University, Masura Mustanov is a new assistant professor, Lulian Ling, and I have on Renko of our postdoc students, and we have Pentti Kujala who is now left Aalto, and Li Fang. There are many people contributing to that tool, and we had also quite a big European Union Winmos 1, Winmos 2, and Winmos 3 is starting. Okay, and the idea is that this wind navigation system is very complicated because we have icebreakers, we have cargo vessels, we have ice, and nobody has even tried to make a system-level simulation model because it's so complicated. But together with Paula, we have started getting in Finland because they won't have a tool. The question is how many icebreakers we need in Finland, and also I know that how many icebreakers you need in Estonia is the same question. Before, it's based on experience, but they wanted to have a tool that can evaluate how many icebreakers we might need, let's say in Sweden, Finland, and Estonia. And that's what we started to build a tool. It started about 10 years ago. We first did the Bay of Botnia, and then we also applied otherwise. And there are many big questions for future. The climate change will have effect to ice, and also these environmental regulations will have effect to the vessels. There's less enzyme power, less icebreaker capability. So what will this have? What kind of effect they have to the icebreaker need? That's a big question we want to answer. And to monitor, I hope they can still see me. This is anything. IPNet is a 10-year-old system that how Finland and Sweden coordinate icebreaker assistance. They have kind of an internet-based system. They get once a day satellite picture of ice, and then you can see the vessels here. This white are icebreakers, and then the color ones are cargo vessels. And you can get the image picture where the vessels are going. and who there's one icebreaker artist in here on the Cargo vessels, and the icebreaker is coming there. So they are very difficult, and that's an idea that what they are using to simulate the current traffic. And our idea now that can we make a similar simulation tool to think about the future, not the day-to-day quest, but background is that similar ideas that we can follow the cargo and everything vessels. And as you can see, the simulation tools have lots of challenges. So that means to open for the people, we have two parameters. It's wave height and wave period. It's enough for everything. But in ice, you can see here that there is 1,000 types of different ice given in this picture only. So we need about 100 parameters to describe ice. It's changing every hour. So we'll come back to that, but that's our challenge. And then every winter is different. Hard winter, last time 1987, when the whole Baltic Sea is frozen. And then we have a very mild winter. We have the ice on east and very north. And then this is like an average style of winter today. So every winter is different, every day is different, every hour is different. So let's make our simulation tool development some challenging. And the simulation model is basically skill image simulation. And we have different ice conditions. We have different deal ways. Deal way means that typically the icebreaker will give instead of a deal way, per way, to go to the easiest ice that they call deal way. Direction way, so how it's coming. And we simulate icebreakers, we simulate cargo vessels, and we simulate towing, we simulate convoys, try to really simulate the whole winter navigation system. And how the more challenging so far has been to make a computer model how icebreaker captains make decisions. So we know that experienced captain knows what they do, but it's very difficult to tell the computer what they think, and we are still working on that, but we have done some interviews and let's see how we do it. But anyway, this icebreaker captain coordination to tell that to the computer has been one of the problems. We have done some validation and so on. In Finland, we have at the moment 6 icebreakers, Puro class, Otsokontio class, and Nordica Pennica class. And then we have actually 7 of the Polaris new ones. So let's say 6 quite old ones. And then the newest one is icebreaker Polaris. Powered vessel built in Helsinki shipyard. So that's our icebreaker fleet. And when we start simulating the navigation in ice, that's you can see an example. This is one vessel, Kemira. My favorite. It's a chemical tanker. I was using that Kemira a lot to make my doctorate thesis, so I spent a lot of time on this vessel. On 1987, 88, 89, I was spending almost all winter always on this chemical carrier. Kemira came from Central Europe to Kokkola and Kaupunki. And here you can see when we are once more, it's open water before they are easy. When we are in open water, it's constant speed, constant power. But it's very easy. But when we come to ice, whatever can happen. But if we are stuck in ice, we wait for icebreaker assistance. We get icebreaker assistance. We stop again. We wait icebreaker assistance to go forward. So it shows how difficult it is. It is now 3 hours, 21, 14, 13, so 16. This can happen in 3 hours. Different events, and our idea is now to make a simulation model that we can simulate all these tough. And that's a basic principle about our model. So we have these derivative stuff. We simulate the hardcore, some derivatives here. And then we have, we call it AP curve. I come back to that, how we define every vessel icebreaker capability. H is ice thickness, V is speed. And ice conditions are ignored by incremental level ice thickness. I will come back to that. And then we can have single assistance, we can have convoy assistance, we can have towing. Convoy means that the vessels are following icebreaker, and towing means that they are towing. They put the rope in and they really tow the vessel through ice. So that's this. It's a typical HP curve. That functional level ice thickness is the thickness and your speed. So typically every vessel is now one icebreaker. So they can break about 2 meter ice. So the speed is 0 after 2 meter. And then we have icebreaker can move after 40, 40 knots. So that's not here. This is now in level ice, and this is channel ice. Channel ice means behind another vessel. Or when we are when it is behind and the broken channel, so the speed is higher than in level ice. So we have for every vessel, we have been developing these curves. So we have about 40 curves for different cargo vessels. Then we know the main dimensions and engine power and how shape we can roughly estimate these HP curves quite quickly. So that's one of the tools we have. See if this works. Very simple about simulator tool. Well, the different alloy is not semantic. It is a different ice thickness. And then we have see that we simulate the whole traffic. Ships are coming, icebreakers are coming, and then icebreakers are helping the vessel to go to the harbor. And then they wait when they come out. So we can, as you can see, that it simulates the whole with the navigation systems. If we have AI data that we know by AI data that the vessels are coming here. And after that, we start to simulate so that we know this starting point and we know how long they are in harbor, and then otherwise we simulate what happened between those events. And then how we have been, there's a lot of work of course done behind. We have a long history actually to how we can simulate ice breaking. So a lot of work behind. I have even educated myself, few doctors. It's slides of my doctor. So what happens when we have a wind? For example, when we have wind, it's planet floating, and this ice breaking will change. So we have simulated that numerically, and then we have the model scale testing. I have to open another file. Let's see. You want ice breaker? Yeah, it's got an ice tank in auto. Very whole screen, but interest. And you now see it. You can see it. Yeah. Because we do it nice. But scale testing is trying as such because we have to scale. The model about the 20. And that's how to scale the ice for the 20. 20 times thinner, ice, and 20 times weaker than real ice. How to make it 20 times weaker. And that's how it goes. Let's get this in. Now I have to change back to them, okay?
Change.
No, this one, yeah. Okay. So the idea is that we have a model scale testing, we have a full scale data, and we have numerical modeling about the ice breaking. So together on this, then we can get the comparison. And here we can see that if we compare now we have a 30 centimeter thick ice measured and simulated, 30 centimeter thick ice and simulated. So we can see the method is a little bit more optimistic than simulation tool. So some difference, 10 to 20%. But I say to everybody that in hydrodynamics, they think that in hydrodynamics 1% is enough. In ice, 100% is always enough. 100% accuracy is always enough. So this 20-30% is still very accurate when we do it something in ice. But anyway, we have done this validation. So we have the ice figure, and then we have been developing for different vessels. We have the database about vessels navigating in the Baltic Sea, especially the Finnish harbors. And for every vessel, we have done similar HV curves. So that's the idea that when we know the main dimensions, you can see that length, breadth, draft, block coefficient, and hull shape, we can evaluate these HV curves for every vessel. That's how our simulation model works. There's some differences based on the hull. And then we have developed a regression formula where we have the main parameters of the vessel, and then we have the main hull angles of the vessel. So that's how our simulation is working. And then we have different vessels that behave different way. Akuas is a very good ice core vessel built in Finland with South Africa. It has a blue curve is a level ice thickness, so in level ice the speed is less, but when you go to the channel ice flows, the speed is higher, so the different curves are different, and although we have a parameter here, this gamma is the channel. Here gamma is 0 when channel is closed, and here gamma is 1 when it's same as a sea breadth. So that's the idea. When you have a very close channel, it's like level ice. So very close channel is the same as level ice. Actually, the channel curve comes to the level ice curve in that. And then different vectors, Elvig is very bad. It's a bulk carrier, but it has a very vertical bow, so it's very bad also in channel. And so every vector behaves a bit different way. So that's one part of a simulation tool. And then this exponent ice thickness is another story. So if you look at the normal ice at here, our idea is that we change whatever ice we have to equivalent solid ice thickness. So we have only one value because all our HV curves are based on speed and equivalent ice thickness, so that we make it equivalent, so that we have level ice, we have new ice, level ice, also rich ice. So then we try to call it equivalent ice. There are many ways to do it. And one simple way is geometrical equivalence. So we start. Then we have, as you know, in rich, we're going to have a say about 10% above, 90% below, because ice density is over 90. So always 10% of ice we can see above the water, and always 90% is below the water. Then we have ice ridges. So the kind of volume equivalent means that we just calculate the total volume and change it to the equivalent thickness. So that's very simple. Only chemical equivalence. It's not physical equivalence. It works sometimes. It give us some value. But then we have different, for instance, we have different methods to do the equivalent like this. But the basic idea is given here that whatever ice we have, we simulate it by level ice thickness. So that's the background for equivalent ice thickness. And then some case studies. I have one case study from to Finland, and then some case study to Estonia. So the first one is done some time ago, one month simulation of ice. As you can see here, we have one Urho-class vessel, one Otto-class, two Otto-class vessel, Ymer, Atele, Freya, Swedish icebreakers, very similar size as this Urho-class. And the ice thickness was about 10 to 45 centimeters in that case. And we simulated 1 month, so we had about 201, let's say, 200 or 300 one A-class vessels in that time, and about 100 1A super ice-class vessels on that area. And what we did, our main KPI is because according to Finnish icebreaker systems, the waiting time of vessel is the KPI. Our government has, because everybody has to pay this harbor fee. It's a very expensive in Finland, but our government is guaranteeing that the maximum icebreaking waiting time is 4 hours. So everybody is following this, how long cargo vessels have to wait icebreaker, and it should be below 4 hours on average. It can be higher, sometimes lower, but it's an average. After the average waiting time should be less than 4 hours, and that's basically works in a normal winter, but on hard winter, the 4 hours is a demanding. But the main result here is that we simulated the waiting time the whole winter, only 1 month period, and when we calculated the waiting time based on our model, we get only 2% difference to the real values. So it was the waiting time seems to work very well. We have some other challenges that this simulated model 2% accuracy is not really true in this waiting time. It works, but sometimes some other parameters, the accuracy is 20-30% or whatever. It's because it's so many parameters, but we are working on that to improve it. But basically, this tool will tell us quite nicely the waiting time, and then we can, that works. And then another interesting story is that what is the total waiting time? And it's today, the total waiting time is about, let's say, totally we calculate all the vessels, 1,300. But when we have this kind of early vessels means that we have less engine power because environmental regulations. So if you have 30% of cargo vessels is 80, the waiting time is about 7,000, 50% early vessels 2,000, and 70% early vessels about 5,000 and so on. So this graph shows that we need more icebreakers because the early vessels are coming, there's nothing we can do. Inside these environmental regulations, so there is more and more environmental friendly vessels who cannot go in ice.
Can I make a question? We had a very good seminar on Kotka last week.
Yeah.
And then one of your students, Alexander, presented his studies where he said that instead of having this waiting time as a KPI, it could also be costs or environmental figures.
Yes.
And that sounded very good. So if these Alexander's ideas are put into this model, we can get totally different results. And it seemed that the Eero Hokkanen.
More icebreakers.
No, we can't start from that. We have to start from the model we made up. And it was very, very interesting. And Eero Hokkanen from the ministry was very interested that we should develop these ideas to have other KPIs. So
Yes.
how do you feel that?
Yeah, of course, it's good idea. The KPI now is waiting time.
Yes,
Yeah,
yes.
but
And we calculate the
Waiting
whole.
time is, it's only one number, it's still easy. But economic KPI and other economic, it gets life very complicated, but it's possible to do more. It's possible to do.
Yeah, and it's very good we have the model, so then we can try out different types of KPIs.
Yes. And of course, the economy, is it you calculate the economy of the single vessel, or you calculate the economy of government, or you calculate the economy of companies, or you calculate the economy of areas.
Yes.
Depends what area. If you calculate whatever economy you calculate, it's a totally different effect. You calculate the economy of Kemi area. Kemi is different than for Helsinki. For
Yes.
example, what is economics?
Yeah, exactly. And then you can try out different kinds of alternatives. And then there was also environmental regulations that how much CO2 they are emitting.
The economy is one thing and CO2 is another. I mean, this tool has been installed for other purposes.
Very exciting.
Yes, but okay, yeah, anyway. But so far, I have a little time on this 85, so. But still, although the economics said that still means that we might need even more icebreakers. Even more icebreakers, that can be possible. Because economically, the icebreaker is the most economic way to do it. That was also one result. So the more icebreakers you have, the less CO2 you have, but the more expensive. Yeah, that's how you calculate CO2, how much you want to pay for CO2 value. If you calculate how we save CO2 and how much you want to pay, so that's better for the rest. Yeah. So anyway, the two can be used. And then the other icebreaker study with Ulla last summer. The idea was how many icebreakers Estonia will need until 2050. That was our task. It's hard. I can come back to that. So, okay. And actually, what we didn't have a simulation tool, so we actually made a fairways for Estonia, and so very busy times. We had a very small time to do it. So our researchers were working hard to change. It's not pay about me to hear, but anyway, so we wanted to simulate every Estonia. Hardcore here and best most of the best graphics. It's included in the simulation tool. And as conditions we get from the Baltic Institute, the Maritime Institute, I think. And then we had, I come back to that, we had actually two scenarios. We have one icebreaker, always one icebreaker per year, or then 1 to 3 icebreakers on the part of Finland. So that was our scenario we were studying. And then, and the idea is that icebreakers are listed the vessels that have been making for long. That's the one simple way to think about icebreaker assistance, and then they can make convoys. And if they weren't shown, in this case, don't, because we have only 2 zones, we have this better and so on, and then a couple of things. So. And then this is our scenarios we were studying, that we have like on Finland, we have primary icebreaker about 30 megawatt total power. So we can have secondary icebreaker 9 megawatt power, and our Finland third icebreaker 6 megawatt, and cavalry got 5 megawatt icebreaker power. So and then icebreaker scenario one, we have only one icebreaker on Finland, one icebreaker on Vilma, or 2 icebreakers, Kalmar Finland, and then 3 icebreakers, Kalmar Finland, always one. And our idea was to study then what happens to the waiting time and what happens to this kind of full consumption. And here you can see we define this maritime institute. We define what is mild winter, what is normal winter, what is hard winter. And then we make evaluation until 2030, 40, 50 that. And the main conclusion is that the probability of hard winters is coming down, but it's not zero. It's even not close to zero. I think the best estimate that we can have hard winter, 10% is hard winters. So once in every 10 years, we still have hard winter. And then more mild winters, more normal winters. But anyway, we cannot forget that we can get hard winter. So yeah. And here is the aspect. As you know, we have Elena, we have Botnica, and we have the Tarmo. And then, as you can see here, we have a protector for the restoration. It's a bug, ice, it's a bug who can break ice. But it's a Finnish company. So that's the present system. So we simulated all these winters using 2018. So again, here the AIS data is so that AIS data, because how many vessels are coming in here or in from east or north. So AIS data will give us how many vessels are coming, and then we simulate after that what happens. Here's the final result. So if we have this icebreaker scenario 1, that we have 2 icebreakers on mild winter, the waiting time is now minutes, so it means that if we want to have this 4-hour waiting time, it means 240 minutes as a KPI. For mild winter, everything's okay. This icebreaker scenario 1 is enough. On average winter, these icebreaker scenarios 2 and 3 are okay, but icebreaker scenario 1, it seems that we get quite long waiting times on that scenario. So it means that 1 icebreaker in Kalmar Finland is not enough on average winter. So, and on hard winter, even icebreaker scenario 2 and 3 are very challenging. So we might, even the 3 icebreaker case, give us quite long waiting time, but it's very short period. The main conclusion from our study was that we did what average winter. For Estonia, we need 1 icebreaker in Kalmar Riga, 2 icebreakers in Kalmar Finland. So that was our conclusion. And then after that, after Arctic and Kulafurp, and they did the economic calculation. But our work was to calculate the waiting time and also calculate how much fuel consumption was. So now we see in future what happens. Is anybody listening to our recommendations from that? What we think is good for Estonia? Okay, and so the conclusion is that we have simulation tool. We are still ongoing. It's very interesting. Nobody else has done nothing like that here all over the world. Nothing similar exists in Arctic or Antarctic. And now we have, as we heard from Mulla, it can be used at the moment only during this waiting time, but we can also think about future environmental regulations. We can think about economic stuff. We can use many purposes, and also actually we can cooperate with Aalto and Taltech to develop the model, because basically it's Aalto University, so it's very open model. So I'm sure Aalto is very happy also to develop it together. Like Ulla's group, we can have actually might be a good idea to think about something, because the economic part is very complicated as well.
It is. It's very interesting. Even the concept of which costs you take into account, just like you said.
good questions. That was a short story about one area. About 45 minutes, so good. Any questions, anybody?
Okay, I'll start. I can continue. I have to stop my questions then at one point if they're coming to me. But first of all, you have come here as a professor of waterways safety management. What does it mean and how does it differ from your previous work? And what you have in mind? What kind of things you have in mind? And how do I say, where is the challenge, the topic you are answering in this professorship?
Yeah, I think safety is safety. Monitoring safety is the same, but of course we have the Baltic has a. You want to change it, but it doesn't actually. It's not very important. Like for me to remember what I want to do. Of course, most important is to understand what is a strong part of Baltic, as I know that Baltic is very strong on its hydrographic, for example. So in hydrography, cartography, and navigation, we didn't have that in Aalto. So that's one important topic, how we can combine that expertise in Baltic, also education and research. And the other very high expertise in Baltic is IT, digitalization, and how to combine IT and safety. So I think I can see a lot of possibilities to make Baltic on, let's say, on these two areas, because monitoring safety is very wide. We can do many things, but Baltic can be international something on this hydrographic part, nautical cartography, navigation part, and then this IT and safety and cyber security. I have at the moment making a doctoral school about cyber security, 10 doctorates, 5 or 15 doctoral if I get money from European Union, and the next deadline is 2 weeks, so very busy times. But the idea is to have 5 doctoral students in Baltic, 2 to Aalto, 1 to Turku, 1 to Åbo Academy, 1 to Turku Applied Science, 2 to Chalmers, and 3 to Grants University. So, and it's a very interesting proposal, and I think we can manage to make it in time. A lot of work. It's a lot of paperwork. But if we get that up and running, then we can combine these IT experts here in Chalmers and maybe Turku, the maritime experts in Aalto and Grants and Baltic. So that's the most important topic at the moment. And the winter time is maybe not so important here as in Finland, but also ice has some importance here. So, and then the new topic is also windmills. So Estonia is very active on this wind energy, and nobody knows what happens to traffic shipping when we have a lot of wind energy coming. The challenges in Bay of Bothnia and between Finland and Sweden, and a lot of challenges in Estonia as well. So my main idea, of course, and then about education, I'm having one course about marine traffic safety, airway safety, and of course put a lot of efforts to improve the education, and then have other courses on this fairway design and so on. But anyway, most important is to find where Baltic can be strong internationally. And the other topics, as I mentioned, that's my main duty. And as I said, my minimum time is 6 years to get my group up and running. I hope I'm still alive after 6 years. That I cannot affect. But it takes time. I mean, it takes time to make academic news.
And Pentti also a member of the advisory board for hydrographic or waterway safety management program in the Estonian Maritime Academy.
So I'm slowly learning what you are teaching here. Yes.
Yeah.
It takes time actually to learn the different what we have in Aalto.
Thank you very much, Professor, for your insightful presentation. My question is related to the economic field mostly. Is it maybe more efficient to reroute this traffic to the warm seas or to develop the ships for navigations in ice covers areas?
What was the other?
Economic question.
What was the other topic?
So is it maybe cheaper to reroute the traffic to the warm seas instead to develop these breakers?
But like Finland, then we don't have anybody. There's no food in Finland. There's nothing in food because we cannot. Finland, maybe Estonia, maybe a little better, but not much better. But for Finland, we cannot make it. We have to break ice. Otherwise, we don't get food. We don't get oil. We don't get cargo. We cannot do it.
Okay.
We are island. Actually, we have to make. It's a good idea, of course, if possible. Like Sweden is easier. Sweden can do it. Norway has no ice. So,
but it is true that the ice conditions in the North Bay of Botnia are much more difficult than here in the south, where the ice conditions of Helsinki are pretty similar to ice conditions of Tallinn. You know, this is the similar area. So of course there has been a lot of discussion, and they are mainly bigger factories up there. The SSAD factories and Outokumpu and those who are up there. And of course, sea traffic, when you have like iron and it's natural way of transporting over there. But then comes the ice discussion. So it's a very hot political discussion, and there are many ideas behind it. But this is the way how it has been working.
And there was a lot of discussion about 10 to 20 years ago how can we make it by train, that ships are coming to the south, and we have a lot of trains.
Mm-hmm.
But it's not economically, as far as we have been calculating, it's not economically feasible. And we don't have enough trains as well.
Yeah.
Probably changing climate conditions.
Yeah, that will help us.
The situation.
That will help us, yeah.
And wind direction as well, because a lot depends on the wind direction. Here, at least, you can have ice in Finland and ice free and open sea in Estonia.
Yes.
Thank you.
It's expensive to go through ice, but we have to do it so far at least.
And if I can ask, you mentioned South Africa.
Mm.
So as far as I know, they use icebreakers only for touristic trips, not for economical reasons, or I'm wrong?
No, they have a station in Antarctica.
Mm-hmm.
They have people on Antarctica. They have to maintain the station, so they have to transport cargo to the station once a year.
Mm-hmm.
And then that's why they need an ice-going vessel. It's also maintaining the station. A lot of research. There's also 100 people on board and lots of oceanographic research the way south and little ice research. Actually, when we started 10 years ago, South Africa didn't know about ice research. They didn't even imagine that somebody can study ice as a professional. But now they have very active research groups. They in South
Scandinavia.
In Cape Town, and in Cape Town, Telebo University, and then this Cape Town University, there are 2 or 3 universities now very active on ice-related topics because of Antarctica.
Mm-hmm. Do they have their researchers there, or
they have a permanent station? Yeah, they have 10 people living all on the year. 10 people living on this South Africa station, and they have typically 1 year, and then the cargo vessel goes there to get them out and put new people in and maintain the station. And so it's also, of course, it's only one vessel doing that, but as you said, mainly it's a lot of tourists actually in Antarctica from Argentina, especially Argentina, and this Chile, and close to the.
From Cape Town also, they have a regular.
But it's a long way from Cape Town, yeah.
Eigo,
Yeah,
going to ask, please.
yeah. I have also one word questions, but I'm in Power Engineering and Mechatronic Institute, so I'm not a marine engineer, but I'm dealing mainly for the robotics and these kind of things. And my question is, do you know if somebody in the world is dealing also with these autonomous icebreakers, or where we don't need to put so many humans in the board, anymore, and then maybe it's controllable over the satellite communications and so on. So it can be make a little bit cheaper to operate with these kind of vessels.
Yeah, there are some research projects and a lot of discussion. But of course, we had to have autonomous ships on open water first. And then when that goes forward, next is ice. And maybe the harbor operations are the first one to start. Because it's ice observation and ice is difficult. So it's difficult for a human being to understand ice, but it's even more difficult to educate computer to understand ice. Where to navigate? It takes time. Definitely, there are many areas where we can also think about more autonomous shipping in ice, but it's coming, and definitely project ongoing, but it takes time.
And also one other questions that maybe for me looks like maybe there is also some other possibilities to break the ice. I think some. I don't know, wave energy or something like that, using like that something, not the ships, this conventional way. Is somebody, yeah.
There has been many ways to do it, but explosions have been tried and whatever. But still, because the ice breaking by cargo, this kind of icebreaker is based on weight, the ship weight. It's pushing ice downwards. And so far, the best way to do it, everybody is doing it the same way. And a lot of patents to do it differently. But in practice, didn't work so far.
Okay.
There are,
Okay.
There are also some ideas in Estonia to push the ice down and somehow make it, but it's lot of discussions, but still nobody has made a breakthrough. But if you have a good idea, I'm happy to think about it.
No, I don't have, but I just think that it's all these kind of vessels are so big that I think that maybe there is some other way. I don't know.
Or maybe to build a ship with a higher ice class.
Yeah.
One is super plus.
Yeah, to make it independent navigation. Yeah. That's another part of the economic story. Then you have a very powerful cargo vessel. It is economic than icebreakers. One addition to our economic.
And all our towing ships have also very good ice classes. Yeah, so they can operate. I think with 1 meter thickness. So ice.
But today the ship owners, they don't want to invest on this because they have icebreakers. So, but if you have some economic benefit that you invest on better ice cold vessels, that can be a possibility that we pay ship owners some money, not to build icebreakers, but we give some money to ship owners to make better vessels. It's one economic equation here. Of course,
One remark. I think about autonomous vessels, the remote controlled vessels maybe will be initially more solution.
Yes, that is coming as well. Yeah. That's the first step, remote control. Yeah. You have people on board, but a little bit remote control. Yes.
Because you underlined, I think, that when you had this communication between the icebreakers masters, so it was quite difficult to determine all those things in the model.
And how do you feel about nuclear-powered icebreakers?
Yeah, that's obviously.
Because that's the way to get the environment started.
Yeah, Russia has a very long history, about 40 years, and they work very well. So it's a good idea for ice cold vessels. But it's a social, economic, it's more political decision. Can you go to harbor or not? At the moment, it's difficult. I think in the Baltic Sea, it's complicated, but it works. I mean, it's safe. I mean, there's I haven't heard any problems in Russia on those, so it's quite safe. It's safe.
Yeah.
As safe as whatever is safe in the management. Good, very good option, and then to solve this environmental problems.
Yeah, there's no CO2.
Because there are no others. Yeah.
Silence. More questions?
Maybe Inga can say what you wait from me. Or, we have a group now. We have a very small group, but Inga is in our group.
I would say that I'm very happy that Pentti now is the head of our small but very perspective team, because these competences what you have now really enrich our capabilities first, because the problem is that it's not only Estonian competence problem, it's just regional competence problem. Because if I go to ELI, this organization, and I did the courses on navigation risk assessment, so they thought that there's one man, Pentti Kujala, who is knowing everything about this, and he developed this methodology. So I would say that we are very happy that you are here, and what you are proposed in your presentation today really will be so unique, and not only for Talte, Estonia, but Baltic states also. And I can see that probably for Baltic Sea and beyond.
Tomorrow we have an interesting lecture at 5:30. One of the young doctor from Aalto will tell what is the future about how to use this hydrographic data, environmental data, big data for future. So that can give us some ideas of what to do together in the future.
Yeah, and also tomorrow, Pentti, you are giving a lecture in the Academy of Science.
Yeah, and it's very, very similar actually, this one actually.
Yeah.
It's sort of version about what I started today.
But it's just demonstrates how important these questions are now, and this topic, especially Pentti already mentioned that I'm doing projects on navigation risk assessment of offshore wind farms, and we could say that nobody knows and nobody addressed the question how the safety is provided within offshore wind farm in ice conditions, sea ice conditions. This is the problem, and now I can say that probably we can just somehow to address these questions and develop within some projects and research, because it's what is needed, and many other countries also like Sweden and Finland, yes.
Yeah.
They face the same challenges.
I have money for one of the doctoral students, so I've been interviewing with Inga, the doctoral student. So sooner or later, I will hopefully have one, at least one, but maybe two, hopefully, to start early next year.
Yeah.
Okay. Pentti. Thank you very much.
Thank you.
And the fervent. No, Pentti. Do you have something more?
No, I don't have.
No, thank you.
I have many paper presentations, but 1 hour is enough for everybody. Next year, another topic, let's see what it is.
Yeah.
So you have once a year, this one, once a year you have this seminar. Everybody will have once a year or no?
I don't know. I think we will do even more seminars, because we don't have so many people now.
Yeah.
So you will not limit your presentation only once a year. Properly.